recording started, I will give you another minute to finish your warm-up before we talk about it. Okay, let's go ahead and start talking about this. So determine if the following data sets are linear. So remember, that's where we kind of have to check to make sure the slope is constant. And my little shortcut way of doing that was to do the little loopy loops and to figure out how the x's are changing and how the y's are changing. So if we look at how the x's are changing, it's going to go up by 1 for this set, and then the next set's going to go up by 2, and then by 3. And the y's are going to go up by 4, 8, right? Yeah, my arithmetic is, yeah, and then 25 and 17 is another 8. So remember, we're not necessarily looking for whether or not these numbers agree, but whether their ratios agree. So the change in y over change in x. So if we look at that for this one, we're going to have 4 over 1 and then 8 over 2. Well, those are both equal to 4, so they match so far. But then in this last set, we have 8 over 3, which is not 4. It's 2.6 repeating. So even though these two agree, this last set does not agree with the first two. So this is not, whoops, let me scroll down a little, not linear. And for as to y, why is the r not there? It is. You can literally just say slope is not consistent. Because that's literally what makes it not linear, is the fact that we have these slopes. 2 of them are 4, but the second one is, the third one is 2.6. So the slopes don't match, so it can't be linear. For the second one, let's see, our x's change by 2, by 1, by 1, and by 2. And then our y's change by 6, and then 3, and then 3, and then 6. And so here, if we go ahead and check our slopes, our change in y over change in x, we're going to have that the first set gives us 6 over 2. The second one gives us 3 over 1, 3 over 1, and 6 over 2. Well, those all reduce to 3, so we do have a linear function here. So since it is linear, I wanted to find an equation for y with respect to x, so that's just going to be our normal y equals f of x. So first thing I need is the slope. Well, the change in y over change in x is the slope, so I've already found that, so I don't really need to do an extra step to find that. We don't have our y-intercept here, so we have to pick a point that makes us happier. I'm going to pick, I don't know, 4, 2. Sure, that's the point that I'm going to choose. Again, no matter what point you choose, you're going to get the same b value, so it doesn't matter which one you pick. But so I have to plug that into y equals mx plus b. So our y is 2, our m is 3, our x is 4. Don't know what b is yet. So 4 times, sorry, something popped up on my screen. Go away. There we go. So 12 plus b. Subtract 12 from both sides. We're going to get negative 10 equals b. So y equals 3x minus 10. And you can always try to triple check yourself by plugging in some of these other values. Like if I take the first point of 2, -4, 3 times 2 is 6. 6 minus 10 is -4. 5 times 3 is 15. 15 minus 10 is 5. So it does seem like it's holding correctly. That's a nice way that you can triple check that you didn't do something wrong in your arithmetic. So if there are no questions on that, I'll hold on for a second in case something pops up in chat. Otherwise, we will go on to our 1.3 notes because we've got to finish that today so that you can finish your homework. And once again, sorry that it wasn't finished on Friday. I do try to make that a thing, whereas whatever your homework's on is done on Fridays. But we're a little behind. All right, seems like there's no questions, so I'm gonna have to unshare this and then reshare the screen that I need for notes. Okay, so we started these notes on Friday and we kind of jumped around a tiny bit for the sake of time. So the first thing we're going to start with is example 2. So to remind us what we're working with here, so remember we're finding average rates of change, which is essentially, it is a slope. So if you want to think about it as calculating a slope, that's a perfectly fine way of thinking about it. So say we scroll down to our example 2 here. Use the following figure to estimate the average rate of change of the number of farms in the US between 1950 and 1970. So essentially what we need this figure for is to be able to find the Y values because, okay, between 1950 and 1970, those are our X values we're going to work with, but we need to know what Y values we're working with here. So we have to use this function to figure out what those values are. And if we look at 1950, oh, things are happening in the chat. Why wasn't it scrolling down? I'm sorry. Sorry, my chat was not, that was my bad. I'll talk about the quiz at the end of class and let you know at the very end. All right, so, and we're good with seeing my screen now that okay, cool. So 1950 is going to be about here. So if I go up to the function there, I'm going to have this point here, which, so let's say 1950, let's say that's approximately 5.2, and that would be million farms. And then 1970 is right there. So if I go up to 1970, you can't see my writing? Ugh. Let me try this again. Oh. Well, yay. So I'm just writing down the these estimated Y values for 1950 and 1970. No, you're fine. So 1970, let's say that's about, I don't know, 2.8 million farms. And I do have to remember that my thing lags, so sometimes I gotta remember to wait a second. So those are essentially the two values we're going to use. So the average rate of change, we can essentially, again, think about it as a slope. So if I have my change in y's, so 5.2 minus 2.8, 8, I started writing 5. And then 1950 minus 1970. Trust and believe we could type those into a calculator to get 2.7 over -20, which is approximately -0.135. Now also units on this. So the units of the slope, it's actually kind of nice because it's easy to walk yourself through. If you ever forget how it goes, just look at the numbers that you have here. So the numbers in the numerator were in millions of farms, and the numbers in the denominator were years. So whatever the units of the numerator are, sorry, the units of the slope are just going to be the units of the numerator divided by the units of the denominator. So we'll have million farms per year. When do we use years since referring to time? The phrasing of that question is confusing me. I'm not quite sure what you're asking. When do we... Oh, are you talking about like how some... used years since 1950 here as well. So if I had used years since 1950, I would have used 0 and 20. I still would have gotten the same answer of negative 0.135. And whenever you're looking at a question and you're thinking, do I use years or do I use years since? It's really a personal preference. Since here we weren't doing too much with those numbers besides just subtracting them, it was kind of just like, let's just use the full year. But if you had changed it to years since 1950, it still would have produced the same answer. So hopefully that. And usually if they want you to use years since something, they will say so in the problem as well. But it's also kind of personal preference. It's just using years since can kind of make the numbers smaller. So hopefully that makes sense. And now that my laptop is back up, but what is happening? Because now, oh Lord. Oh no. Okay, sorry about that. Virtual learning is fun, isn't it? Yay. Okay, now I'm back. So example 3. Polychlorinated biphenol, if I read that correctly, PCB, is an industrial pollutant thought dangerous to wildlife. The following table shows data on PCB levels and the thickness of pelican eggshells. Find the average rate of change in the thickness of the shells as the PCB concentration changes from 87 parts per million to 452 parts per million. Give units and explain the sign of your answer. So one thing I want to say is something about this phrasing. So find the average rate of change in the thickness of the shells as the PCB changes. So sometimes, now this one nicely falls out in the way you kind of want it to, but if it's ever phrased like this, you want to triple check that you're doing it in the way that they're asking for. Whenever it says, how can I say this generically? Let's say A as B for average rate of change. If it ever says find the average rate of change for A as B, and I should even say changes, but I ran out of space. That says changes. So A as B changes. This is going to give you change in A over change in B. So if it ever says find the average rate of change for something as this other thing changes, the thing that's changing, said to be changing, is the denominator value. Hopefully that makes sense. But in this case, it's kind of nice because it works out kind of exactly how we want to, where the top thing in the table is acting as our x's and the bottom thing in the table is acting as our y's. So we want to find the average rate of change for the 87 and the 452. So we have those two data sets, so now we just have to find the average rate of change. So again, I personally like to put the larger y value first, but whatever floats your boat. So I would do 0.44 minus 0.14, and then 87 minus 452. Oh, sorry. I thought my notes were wrong, but they're not. This is going to give you 0.3 over negative 365. And this is going to reduce to negative 0.00082. Now let me focus again on the units. So the units of my numerator were the thickness in millimeters, so it's going to be millimeters per, and the denominator was the concentration in parts per million. So technically you can write it out in words, millimeters per part per million, but that's a lot of phrasing, so you can always just use the abbreviations as well. So those are our units, but then it also asks us to explain the sign of the answer. So it's a negative. So what that is going to tell us is, so the negative means, now again, this is telling us about how the thickness of the shell is changing as PCB changes. So this is going to tell us that the thickness of the pelican egg, so the negative means the thickness, pelican eggs, is, what do you think the negative means? That's going to tell us that it's decreasing by that value of 0.00082 millimeters per part per million. Essentially what I kind of wrote here, I can highlight or not. Never mind, I can't highlight. This last little bit here is very familiar to the interpretation of the slope in the rate way, which again, this is a slope. So if you ever want to interpret the average rate of change, it's just like interpreting slope. But so just like we were, when we interpreted that slope a while back, we were saying that it was decreasing by the slope amount. That's kind of exactly what's happening here. And the negative is telling us that we're decreasing over time instead of increasing. Erase that so that it doesn't get in the way. So hopefully that makes sense. So wait a couple seconds just in case there's a question. Okie dokie. So then the other day we talked about the average velocity, which is essentially the exact same thing. It's the average rate of change just in the very specific situation of a position function. So let's go ahead and see an example of that. So consider the following table, which shows the height of a grapefruit above the ground t seconds after it is thrown. So say I want to find the change, so just change, and then the average rate of change of the height of the grapefruit in the first 3 seconds. So if I think about what it means for the first 3 seconds, that's going to tell me that it's between t equals 0 and t equals 3. So I'm essentially using this data set here and this data set here. So now the first thing I'm asked for is literally the change. That's all it says. So what it means by that is it literally wants to know how much the height changed by. Like what is the difference between the starting height and the ending height? So for our change, just generic change, this is just asking for the difference in height. So let me say change in height just to try to be clear. Well, at 3 seconds, we're at 162 feet. And at 0 seconds, we were at 6 feet. So the change in height would be 156 feet. And well, what does that actually mean in context? That means that between that time, the grapefruit is going to go up 156 feet. It started at 6 feet. It goes up 156 feet to end at 162 feet. So the grapefruit goes up 156 feet. Maybe I should even be even more specific and say in the first 3 seconds. That would technically be better of me to be very specific. But that was just asking for literally just a change in height, nothing to do with average rate of change yet. Then we're asked to find the average rate of change. So now for the average rate of change, we have those 2 points. So we have to find that f of b minus f of a all over b minus a, essentially the slope. So we've got 162 minus 6 all over 3 minus 0. So that's going to become 156 over 3, which is 52 feet per second. And now we want to interpret that. Well, let me scroll back up really quick to remind ourselves of something we talked about the other day. I'll scroll back down in just a second. So remember, the other day we said that the average rate of change isn't telling us exactly what's happening. It's telling us that on average, this idea here, on average, what's happening in that time interval. Okay, it's not telling us that we're going exactly that much for exactly that entire time. But so essentially, when you want to interpret the average rate of change, again, you can interpret it as a slope. But in this case, it's kind of easier to say something like on average during the first 3 seconds. The grapefruit is traveling. Is that 2 L's or 1? I can't spell either. That looks wrong. Might be 1 L. I don't know. Spell it correctly. In my notes I have 1 L. Who knows? Traveling at 52 feet per second. So I'm not saying it's traveling that fast the entire time. I'm saying on average, during the first 3 seconds, the grapefruit is traveling at 52 feet per second. Okay. So pause for a second. Okay, so say I wanted to find the average velocity of the grapefruit over the time interval t equals 4 to t equals 6 and explain the sign of the answer. So again, just to clarify, so in the part 1, I did say average rate of change, and in part 2 it says average velocity. It's the same thing. It's just using the very specific verbiage of velocity because of the fact that we have a distance function. But I could still have technically said average rate of change again and been perfectly fine. But we're looking for the average rate of change between 4 and 6 now. So again, that's just, think about it like a slope. Excuse me. So we've got 150 minus 30. 4 minus 6. So that's going to give us 120 over negative 2, which reduces to negative 60 feet per second. So, okay, now it wants us to talk about the sign of the answer. Well, what the heck could negative mean in this context? Well, whenever you're talking about velocity, if you've taken a physics course, you would have seen this a lot. When we're talking about things going in different directions, we need to be able to tell whether it's going in one direction versus the other. So essentially what's going to happen here is whenever we have a negative velocity, we're going to assume that to be traveling downwards. So if it's got a positive velocity, it's traveling up, and if it's got a negative velocity, it's traveling down. So essentially what this is saying is the negative means it's traveling, and again, 1, 2, or L, 1 L or 2, I don't know, downwards. Which if you think about this data set and you look at the numbers, at t equals 2, it's 142, then 162, then 150. So it hit its peak somewhere between there, somewhere after 3, or maybe before 3, maybe it went higher than 162, I don't know. But it made its peak somewhere in there, and then it must have started falling back towards Earth. So once it's traveling back towards the ground, it's going to have this negative velocity. So that's what a negative means whenever you see negatives in terms of velocity. Don't panic and think you can't have negative velocity. You can. It just is telling you the direction in which you're traveling. And usually, if you're talking about right to left, usually traveling to the right is positive and traveling to the left is negative. But also, whenever you're talking about a problem, if it needs to be specified, it usually will be. So I know there are a few problems in the homework. I don't think in this homework, but in homeworks to come, that have velocity functions, and you have to talk about the negative velocity versus the positive velocity. And they usually specify positive velocity means moving this direction. And while they might not specify the other way, because if they specify the one way, the other way is obvious. But they will specify which way is counted as positive. Okay. Hopefully that makes sense. So we've got one more with the idea of average rate of change, and then we've got two other small little topics to talk about in 1.3. So say we have a car that travels away from home on a straight road. Its distance from home at time t is shown in the following figure, and is the car's average velocity greater during the first hour or the second hour? Well, okay, so average velocity, so I'd want to be able to compare, those values, but I don't have any y values here, so I can't actually calculate the values. So how the heck am I going to compare these things if I don't have the actual values? Well, we have to go back to the idea that an average rate of change is technically a slope. It is the slope of the line between the 2 points that you care about. That's what we were explaining up here on Friday. It is the slope of a line between the 2 points that you care about. So why don't we use that idea? So, okay, coming back here. So let me split this graph up a little bit, or at least give us some, nope, that's too far over. 2 goes up there. Okay. So we've got the first hour would go from 0 to 1, right? So let me draw the line to the best of my ability between those 2 points. So we've got the first hour there, and then the second hour would be from 1 to 2. And if I draw to the best of my ability, it almost follows that line, but not exactly, but it is going to follow that curve pretty closely. And so now we've got these two little line segments, one in the first piece and one in the second piece, and I have to figure out which one has the larger average velocity. Well, again, so the average velocity is representing a slope, so I need to look at which one of these two line segments has the larger slope. Which one is, I should be careful about saying it like this. Because they both have positive slopes, we can look to see which one's steeper. So since they're both positive slopes, negative slopes gets weird. But since they're both positive slopes, we can look at which one's steeper. Well, which one's steeper? This one right here. It's got a bit of a steeper slope to it than the other one that's going a bit, it kind of levels out a little bit. So this is going to have a greater average velocity in the first hour. And I'll just give a short explanation just so we remember why. We can tell because the slope of the line between 0 and 1 is greater than that of the line between 1 and 2. So since that line segment in that first hour has a steeper slope than the second one, we know that the average velocity must be greater during that piece. So you don't necessarily even need to know the values. If you can compare the steepness of the lines, you're still able to compare average rates of change, average velocity. And that's kind of an important detail. Any questions about average rate of change? Because we're about to go on to something different. Alrighty. All right, cool. Whoops. Okay, I'll just leave it there. So the graph of a function is called concave up. If it bends upward as we move from left to right, and I'll kind of show what I mean by that in a second. And the graph of a function is what we call concave down if it bends downwards as we move from left to right. A straight line is neither concave up nor concave down. A straight linear line does not have any concavity. So here are our choices. We have whoop, and we have whoop. I made those very large. So this is going to be concave up, and then this is going to be concave down. And then kind of in each one of these, we kind of have two choices as well. We can kind of break up each one of these into two sections. And each one's going to have one piece that's going to be decreasing and one piece that's going to be increasing. So the concave down, this piece is increasing, this piece is decreasing. Now, we present the idea of concave up and concave down in this section right here, and it's kind of introduced, and then it feels like it disappears for a while, and then it pops back up in chapter 3, maybe 2, but in another chapter. So we do kind of come back to this idea once we get derivatives under our belt, but we kind of introduce it now. So here's what's going on. Now, this piece and this piece, I think, are easier to see, maybe not easier to see, easier to understand why they are concave up and concave down. So concave up means that it's bending upwards as you move from left to right. So that's why I think this side is a bit easier to see. If you just kind of look from left to right, it looks like it's bending upwards, right? Whereas this other side, it might not be as obvious. But here's essentially what's happening. If you think about the, you don't know that wording. I was going to say tangent line, but you don't know what that is. So say I draw a bunch of lines that kind of follow the shape of the graph at that very point. So if it were like a roller coaster and it broke off, where would it go if I continued on forever? So let me erase the ones that I just did and do one generically first. Whoops, 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 whoops. So say I look at this point right here. If this were a roller coaster and it were to break in that direction, you know, this would shoot off in this way, or, you know, they'd shoot off this way, depending on which way they were coming from. A little bit morbid, but if it was a roller coaster and it broke, you know, it would follow that, and physics didn't exist. They would go off in that way forever. And if we think about what's happening with those lines as we look at them in different, it's frozen. Did my internet pop out again on my laptop? No. Let me finish drawing this really quick. And then let me unshare and reshare, and hopefully that will unfreeze it. See things now? I've got 3 little blue lines drawn on it. Okay, cool. So if we look at these blue lines, they're getting less and less steep, right? Okay, looks fine on your side. Well, now it seems to be fine on everyone's side, so hooray! So if you look at those blue lines that I've drawn, they're kind of getting less and less steep as you go from left to right. And that's kind of what we mean by bending upwards in this manner, is that as we move from left to right, the slopes are getting more positive. Now they're negative slopes, so becoming more positive means that it does get less steep. Also, if you think about it in terms of like, so let me erase these, they're clogging it up a little bit. So if you think about it in terms of like, imagine that this, you know, parabola is showing, you know, you're flying a helicopter and this parabola is showing where your helicopter is. If you're traveling along this side, you know, and you're about to crash into the ground, you're trying to pull that helicopter upwards, and that's exactly what your helicopter would look like, is it would start, it doesn't immediately go upwards, it's got to like slow down a little bit before it can start going back up. But if you think about it, if you're heading down towards the ground and you're pulling the helicopter upwards, that's kind of what we mean by bending upwards. So that's a lot of hoopla to just say it. I shouldn't say a simple concept, it's not that simple. And then concave down, so this side, I think it makes a bit more intuitive sense that that's bending downwards, whereas the left side, it's kind of the same thing. You're flying a helicopter, you're going up, but you want to land. Well, you kind of have to, you know, slow yourself down first before you can start going downwards. So that's what we mean by bending downwards, is we have these, you know, if I draw my little lines again, these slopes are getting less and less steep again too. So it's kind of leveling itself out before it can go back downwards. Another way, if that's way too complicated, one of the ways lots of people go about trying to remember these is concave up like a cup and concave down like a frown. And then you can just literally draw these two pieces and look at it. So that's what a lot of people do instead of trying to think about it too hard, is they just do up like a cup and then down like a frown. So if that works, whatever floats your boat. So that's concave up and concave down. So let's look at this example down here. Using the following figure, estimate the intervals over which the function is increasing or decreasing. So we already know how to do that. And then new thing, concave up, concave down. So let's do increasing or decreasing first. So increasing or decreasing, that's going to change, when it changes direction. So it's going to change here. And let's just say it changes at 6. It looks like it changes slightly after 6, but for ease, let's say it changes at 6. So we're going to break it up here and here for increasing and decreasing. So in that first piece from -infinity up to 2, we're increasing. That second piece from 2 to 6, we're decreasing. And then from 6 to infinity, we're increasing. We're just going to assume that this continues on forever in both directions. And again, if you wanted to put brackets on all of those except the infinities, that's perfectly fine. So now, new idea, this concavity piece. My biggest tip for finding intervals on when something is concave up and concave down is to look for these types of pieces. A concave up piece and a concave down piece. So if I look at this piece right here and this piece right here, those two kind of resemble, that one resembles this one and this one resembles that one. Those two resemble those types of pieces, right? And there's no more pieces of that graph that look like those. So once I kind of figure out where my graph looks purely concave up and purely concave down, because the ones I drew were gross looking, now I can start to figure out my intervals. Concave up, concave down. So again, there's no other places in this graph that look like one of these two pieces besides the ones I already have boxed off. So once you kind of box off the ideas of which ones are purely concave up and purely concave down, once you've got all those in your brain, you've got the sections you need. There are going to be no more sections than boxes. So since I have two kind of boxed off areas, I'm only going to have two intervals, if that makes sense. So this first box over here, that thing that I have boxed is definitely concave down. In that little boxed off piece, that definitely looks like a concave down thing. So what that's going to mean is this piece is going to be concave down. But then if I look at the other box definitely resembles this kind of idea. Well, that's up like a cup, so this piece is concave up. Well, what about all the other stuff that's not boxed? Well, if it's to the left of this concave down box, that's just going to continue being concave down because, again, there's no place where it's going to change. And to the right of this concave up box, everything's going to be concave up. So the only real ambiguity is what the heck is happening in here? Well, it's got to change somewhere in there. Now, finding the exact place where it changes from concave up to concave down at this point in time is incredibly hard. Okay, eventually we're going to have a process that's going to allow us to figure it out algebraically, but for right now we just have to estimate it. But it's got to be somewhere between those two kind of boxed off areas, so let's go ahead and just say for ease that it's going to be at 4, because that's kind of about halfway between the peaks. So we're going to say that this breaks up at 4. So we've got that this first box is concave down. So that's from -infinity all the way up to 4. But then from 4 to infinity, it's concave up. Just like with, increasing or decreasing. Put a bracket on there if you want to, whatever floats your boat. I usually just default to parentheses everywhere, but same thing. Just like saying something's increasing, decreasing, or constant at a singular point doesn't make sense. Saying something is concave up or concave down at a singular point doesn't make sense. It has to be over an interval that you're talking about to make sense about talking concave up, concave down. That makes sense? Slowly running out of time, so I've got to start huffing a little bit. All right, example 7. So we're going to go through this somewhat quickly just so that I can get to the definition of relative change. So from the table, is it increasing or decreasing? Do you think it's concave up or concave down? So increasing or decreasing, well, that's going to be talking about our y values, right? Are our y values increasing or are the y values decreasing? Well, if we look here, the y values go up by 0.5, go up by 1, go up by 2.1, and I know I'm going through this a little fast. Go up by 3, that's not right. Yeah, 3.8, sorry. Go up by 9.6 and go up by 13.1. So I was just finding the differences between those y values. These y values, so I shouldn't have done that yet. That was going to be the next thing. But anyway, these y values are increasing, right? Since all of these values down here are positive, that means we're increasing over time, right? So since the y values are increasing, that means we're going to be, the function is increasing. So to tell whether, something's increasing or decreasing from a table, just look to see whether the y values are increasing or decreasing. Concave up and concave down is a bit more complicated, but that's why I actually wrote out these little values here. So those values, well, I should be even more careful. If I go back and I do my changes in x's, those all increase by 5, okay? So what you want to look at for concave up and concave down is the slopes. So the slopes would be 0.5 over 5, 1 over 5, 2.1 over 5, 3.8 over 5. I'm taking those change in y over change in x's, 9.6 over 5, and 13.1 over 5. Now I could, of course, type those all into a calculator and find the actual decimals, but for the sake of time, those numerators are increasing, the denominator staying the same, so the entire value must be increasing, right? So our slopes are increasing. My pen decided to stop working at a really inconvenient time. Increasing. So if the slopes are increasing, it's going to be concave up. So let me make a little note in a different color to denote that it's just a general note, not for this particular question. So if slopes are increasing, it's going to be concave up. And if slopes are decreasing, it's going to be concave down. So I know I went through that pretty fast, but it's because I got to get to this very last thing. Questions on that? Really quick. Alrighty. Last thing, it's not too bad. So think about populations. If you had a population change of 1,000 people, would you notice? And that probably depends on where you're at. If you're in Coyote, actually, what is that? New Mexico? So say you're in Coyote, New Mexico, which had 128 people in 2017. If their population increased by 1,000 people, they would notice. But if you're in New York City, which had a population of 8.5 million in 2017, pretty much no one would probably notice an extra 1,000 people moving in. So kind of this idea of is it noticeable, is it not, is kind of going to depend on what value you started at and what value you ended at. So say we have a quantity P and it's going to change from P naught to P sub 1. We're going to define the relative change, and that's going to be the change in P over whatever P naught was. Or you can think about it as P sub 1 minus P sub 0, or P naught, divided by P naught. So what would that look like? Now, the relative change is a number without units. So the nice thing is that you don't have to worry about units for relative change. My eye disappeared. And relative. It's also usually changed to a percent at the end. So you calculate it as a decimal and then you change it over to a percent usually. So let's say we wanted to find the relative change in the population for Coyote, New Mexico, and then New York City if the population changed by 1,000 people in 2017. So if we start with Coyote, well, we were told in the original statement right above that I have scrolled down past now that they started at 128 people in 2017. So that means they went from 128 to 1,128. We don't care what time frame it happened in, we just care the starting value and the ending value. So this was the starting value, so that's P0, and the ending value is P sub 1. So it's always the beginning one, whatever you started with is P0, ending value is P sub 1. So our relative change is going to be P sub 1, the 1128, minus P0, so minus 128, over the original value of 128. Trust and believe we could type that into a calculator. This is going to be 1,000 over 128. So 7.8125. Now again, so this doesn't have units and it's usually expressed as a percent. So if you forget how to change a number to a percent, what you're going to do is you're going to take the decimal and you're going to move it 2 spots to the right. So this would be 781.25%. So their population increased by 781.25%. That's a lot. They would notice. Whereas if we did it in New York City, they started 8.5 million in 2017. Oops. And then they ended at 8.5 million, but 1,000 more. So you would take, again, so the starting value is 8.5 million and the ending value is that extra 1,000. So if we have the ending value minus the beginning value, how many zeros do I need? No, that comma's in the wrong spot. Boink. And 2 more, there we go. Dividing by the original value. Yes, I will say that in just 1 quick second. I know I'm going the tiniest bit over. I'm almost done, I swear to God. This would be 0.000117 blah blah blah, which would convert to 0.0117%. So sorry, I'm supposed to be done right now. So that's how relative change goes. For the sake of time, like we need to be moving on, I'm not going to do the rest of these problems. I will put the full notes on Blackboard. It's just the same idea, just 2 more examples of it, the same idea. Your quiz on Wednesday, super duper quick. Your quiz on Wednesday, linear, nonlinear, so just like our warm up today, and then average rate of change. So let me type that in the chat so people can find it later. So quiz on Wednesday, linear / nonlinear, and writing linear equations. So like the warm up, I shouldn't have pressed enter yet, and average rate of change. So average rate of change, linear, nonlinear. Sorry for keeping you a minute late. Stay if you have questions. I can hang around for a little bit. I know I went through that last bit really quick. But thank you for your patience. Let me know if you have any questions on the homework, especially the relative change stuff, because we couldn't get through much of it. Have a good day. I'm going to stop the recording now.